All right. So lastly, with XPS and AES, I want to talk a little bit about how we quantify uh, the composition in these two cases. So let's start, well, actually with both. So the same general formula uh, can describe the composition in both. So here's our general equation for the fraction of a given component. And you'll see, as in other analyses that we've done this semester, the peak intensity is going to tell us relatively how much of a specific component we have. So I sub I, capital I, is the peak intensity for that component I. And then we're going to divide by what we term a sensitivity factor of I, and that's capital S sub I. So these sensitivity factors are tied to the specific element and also corrected for a specific spectrometer. And so these are typically things that are either going to be in the software if you're using the software that goes along with the instrument, and you can also find them tabulated as well. And I've actually got values in that same PDF that have sensitivity factors for both XPS and AES. So you can find that. And so basically, it's a ratio of peak intensity to the sensitivity factor of a component over the sum of all of those fractions. And that gives us our amount. So let's look at it for XPS. So peak intensity, what we term this peak intensity, is the background subtracted peak area in XPS. So here's an XPS peak. We've fitted that Shirley type background, and we found the area underneath the curve, which is shaded gray here. So that's the peak area. And so we're going to use that as the peak intensity when we're talking about XPS, right? So XPS, we're going to use background subtracted peak area. So now let's look at AES. So AES, we saw that the typical mode that we're looking at is actually differential mode, right? Where we take the differential of the signal. And so in this case, we don't really think about the area in these types of curves because we have a positive and a negative component potentially. So in this, the peak intensity is going to be calculated as the peak to peak height. So we have a peak here at the positive, we have a peak here at the negative, and so that's peak to peak, that's the height. And so that is going to be used as the peak intensity. So the peak intensity the amount of component we have for XPS and AES has the same equation. The only difference is the peak intensity is peak to peak height for AES, and then going back here, peak area for XPS. And you're obviously going to find different sensitivity factors for AES and XPS of the different instrument you're using, the spectrometer, and the different elements that you're using. So all of that will be dependent as well on the instrument, but same general formula. Okay, so here I've given you a pattern. I'm not going to tell you which one it is. Hopefully you can figure out XPS or AES based on what you're seeing there. And see if you can estimate the atomic fractions of aluminum and oxygen in the spectrum. So you can kind of ignore the carbon that we see here. So just aluminum and oxygen. See if you can estimate based on the information given and the sensitivity factors. So you're going to have to go back to that PDF and you'll find sensitivity factors for XPS or AES, whichever one you need, and also for whatever element it is. And so see if you can go through and estimate what that is. Get as close as you can. I know it's up here on the screen, so you might have a little difficulty, but just, estimate, and we'll come back and I'll show you what I got for this. All right. So let's take a look at how we estimate these atomic fractions. So as hopefully you were able to determine from this plot, this is AES, so Auger. And you see those KLLs in that for all of these actually. So those three letters obviously point us to an Auger transition. So that means that we're going to look at peak to peak height. And so I measured this. I actually measured this using a software on the computer. So it's going to be probably more accurate than you got, but don't worry about that. We're just trying to get close. And so I measured this peak to peak height, and that's going to be my intensity. Here I used units of inches. What we're going to see here in a second is that the units don't matter as long as you're consistent. So that's why I'm not really worried too much about the inches. If you have intensities markings up here, you can use that. That's fine. But I didn't have anything, so I just used inches that I measured because I'm trying to get a relative amount. So that's the first part. Also, in that table, in that PDF document about surface characterization, you should see a sensitivity factor for AES, and it's graphed, so it's a little harder to read. So for oxygen and aluminum, I've tried to highlight those two values here. So this is the way you're reading this is x-axis down here is atomic number. So you're going to find it for oxygen and aluminum, and then find where that is on the curve, and then get the sensitivity factor. And that sensitivity factor, you'll have to kind of look at the scale and see that it's in log. So it's going to be a little harder to read. But getting those approximations, I got that the sensitivity factor for oxygen is around 0.8. So again, essentially right here. And then aluminum, which is down here, is closer to 0.4. So I'm just reading these tick marks and getting an approximate. And so that's probably as good as we can get from these graphs. And so then I'm going to plug it in to our atomic fraction expression. So all of those values, again, keep in mind that these are in inches, but it's going to cancel out. And so when we plug all this in, we get that the atomic fraction of oxygen is 0.316, and the atomic amount of aluminum is 0.684. Right? So that's how we can use this. If it was XPS, similar procedure, but we're going to get the peak area. So that's a little harder to do while you're looking at a slide here. So we went with AES. So that's how we're going to calculate these things. So obviously, if I give you a homework problem or something like that, then maybe we do XPS where we have to get peak area.